And let's talk about covalent bonds. In this case, we're going to talk about nonpolar covalent bonds, where the attraction between the electrons is going to be equal. To have a true covalent bond, you must have two atoms bonded together where the attraction is going to be exactly equal. And technically, the only way that this can happen is if you have two atoms that are the same type of atom bonding. Oxygen, hydrogen, fluorine, all of the diatomic molecules that we have, these would be considered purely covalent bonds between the atoms. What this also means is that when that bond is formed, the electron cloud is equally distributed. You'll see here that we have an equal distribution of the electron cloud around these 2 points. The two positive signs represent the nucleus. The chemical bond then would be the area here where you get the highest density of electrons. That represents where the electrons are being shared. Although this entire cloud is where the electrons may be, the higher area of probability is where we could consider the bond to be. But the thing is, since it is equal sharing on both parts of the atoms, the distribution of the electron cloud around them is equal. An example of something that's going to be really close to being a pure covalent bond is carbon with an electronegativity of 2.5 and selenium with electronegativity of 2.5. Since they are not exactly the same element, there is going to have to be some imbalance in the attraction between the electrons. Even though they both have electronegativity values the same, there's going to be the very slightest variation, although we could probably consider that to be a nonpolar covalent bond. Polar covalent bonds are going to be caused by an unequal attraction for the electrons. That means that one of the atoms is going to have a higher electronegativity than the other atom. So any difference in electronegativity is going to cause some polarity to occur within the bond. What that means then is that our electron cloud is going to be unequally distributed, where we're going to have a lower density of electrons around the atom that has lower electronegativity and a higher density around the atom that has a higher electronegativity. In this case, the bond between hydrogen and chlorine would have a lower density or lower probability of electrons around the hydrogen and a higher probability around the chlorine because of the fact that the chlorine has a higher electronegativity. For polar covalent bonds, we have a very wide range of electronegativity differences we can have. We can have an electronegativity difference of 0.3, and that would be a bond between hydrogen and carbon. We could go up as high as and have a polar covalent bond with electronegativity difference of 1.8 when we have hydrogen bonded to fluorine. An ionic bond then is just going to the other extreme, opposite of what the nonpolar covalent bonds are. It's caused by a transfer of electrons, and one atom is going to have to be significantly higher in electronegativity than the other. The significantly larger electronegative atom is going to attract the electrons from the lower electronegative atom. In this case, we have sodium giving electrons up to the chlorines. When that happens, we form the ions of sodium ions and chloride ions. Now in this diagram, we can see that sodium's atom size has significantly decreased and chlorine's atom size has significantly increased. That occurs because of the transfer of the electron. We now have the sodium cation, positively charged ion, and we have the negative anion of the chlorides. All of those now are going to be attracted to each other because of the opposite charges. Bond length and bond energy are two properties of bonds that we're going to look at a little bit closer later in this unit, but I want to introduce them now. Bond length is pretty simple. It's simply the distance between the two nuclei of the atoms that are involved in the bond. So if you simply measure the distance between the nucleus of one hydrogen atom and the other hydrogen atom in an H2 molecule, you'll see in this diagram here, we would get 74 picometers. If we measure the distance between the two iodine nuclei, so we've got iodine, a nucleus here and a nucleus there, the distance between those of 266, that would be the bond length in the I2 molecule. Bond energy is simply the amount of energy that's released when a chemical bond is formed. Here we see that we've got 4 hydrogens. Those are all going to be bonded to nitrogen, and the 2 nitrogens are going to be bonded to each other. When this molecule forms and these atoms form these bonds, you'll see here that we get energy represented being released by these arrows pointing outwards. Now, the negative 389 value is the amount of energy that's being released by the formation of the hydrogen and nitrogen bond. You'll notice since we have 4 hydrogens being bonded to those nitrogens, we have 4 different values of the 389 to represent each of those bonds that are formed. The negative 163 represents the energy released when the 2 nitrogens bond to each other. All of those together, added together, would be the amount of energy released when that compound into H4 molecule is formed when those atoms bond to each other.